This is the second class on the unit waves. Okay, so in general, what do we mean by wave motion? It is the propagation of a disturbance. This can happen in two ways. Propagation of a disturbance disturbance means energy, some energy. Propagation of a disturbance or energy through it can happen. This propagation of energy can happen through a medium. Okay, for example, waves on water surface, waves on a stretched string, sound waves. Sound waves are waves through air. So in this situation, in this type of a wave motion, the particles of the medium, the molecules or the particles of the medium, they do not undergo any displacement from one point to another. They just oscillate about their mean position. Okay, it is the energy that is getting transformed. What is being moved or transferred is the energy or that disturbance or that energy. So in that sense, wave motion is the propagation of an energy. Okay, this can happen through medium. It can also happen without any medium. For example, electromagnetic waves passing through vacuum. Electromagnetic waves do not require any material medium for propagation. Light is an example of electromagnetic waves. There are other electromagnetic waves. They can propagate through vacuum without any medium. So wave motion can happen either through a medium or through vacuum. In the previous class, in the first class on this unit, we have seen that if you consider a progressive wave, a traveling wave, progressive wave means a traveling wave passing along plus x direction. Consider a wave traveling along one direction, one dimension. So if you consider a wave traveling along plus x direction, then its a wave function we can write as, it depends on position as well as time. We can write as a function of x minus vt. Like this we can write. It's a function of, it depends on position and time in this combination, x minus vt, where v is the wave velocity, or it is also called phase velocity. And if it is a simple harmonic wave, this function we can write as a sine function or cosine function. Okay, and we have seen this formula, a sine function or cosine function 2 pi by lambda into x minus vt. So you can see that this x minus vt comes in the phase. This 2 pi by lambda into x minus vt is the phase angle of the wave motion, and in the phase angle, position and time appears in this combination x minus vt. This shows that the wave is traveling in the plus x direction. How we can deduce that is in the plus x direction? That for that you refer to the previous class. There we have used physical arguments to arrive at this expression. And if it is a wave traveling in minus x direction, then what you get is, it's a function of x plus vt. The position and time combination appears as x plus vt. Okay, so this expression can be considered as the equation for a simple harmonic traveling wave along positive x direction. It can be cosine function also. Here v is this velocity, v is the wave velocity or wave speed. Another name is phase velocity or phase speed. Okay, and lambda is the wavelength. Okay, and this velocity and lambda are connected by wave velocity or phase velocity, and lambda are connected by this formula, v is equal to mu lambda, as you know, where nu is the frequency of the wave. Then some other relations, connected relations are 2 pi nu is called, nu is the frequency, 2 pi nu is called angular frequency. The difference is that nu is measured in terms of hertz or cycles per second. Hertz or cycles per second. One cycle per second is called 1 hertz, named after Henrik Hertz, who first produced and detected electromagnetic waves experimentally. And this omega is angular frequency it is measured in the unit radian per second, or simply second raised to minus 1. Okay, so another and also this 2 pi by lambda is called wave number k. Okay, 2 pi nu is angular frequency omega, and 2 pi by lambda is wave number k. So this omega and k can be connected. If we calculate omega by k, okay, then what you get is nu lambda. Okay, that is omega by k is nothing but, we know that frequency times wavelength is phase velocity, so we have a relation omega by k is the expression for phase velocity. Or phase velocity you can either express in terms of frequency and wavelength as nu times lambda, or in terms of angular frequency and wave number as omega by k. These results will be useful when you do the calculations. Now the expression for progressive wave, this formula we can rewrite and write in many different ways. Let us consider a few ways of writing this equation for progressive wave. Instead of 2 pi by lambda, if we substitute k, we can write this as a sine k into x minus vt. This is one way of writing. Let us call this as equation 1. Let us say this is equation 2. And another possibility is, let us multiply this 2 pi by lambda in equation 1. Let us multiply 2 pi by lambda with these two terms here. Let us open the bracket. Then we can get another formula. So from equation 1, the wave function you can write as a sine. So I am opening the bracket. Let's go back to equation 1. So I am multiplying 2 pi by lambda with these two terms. Okay. So we have the first term is, let us open the bracket. The first term is 2 pi by lambda times x minus 2 pi by lambda times vt. Okay. Now this you can write as 2 pi by lambda is k, alright, so it is kx minus, and 2 pi v by lambda. V by lambda from this equation, look at here, v by lambda is frequency. So here we get 2 pi by lambda into v by lambda is frequency, we get 2 pi nu. Now what is 2 pi nu? Look at here, 2 pi nu is omega, angular frequency. So the second term will be omega t, equation 3. So this is also a commonly used form to describe a progressive wave moving along plus x direction, a sine kx minus omega t. Okay, so either equation 1, 2 pi by lambda times x minus vt, or equation 2, k times x minus vt, or equation 3, kx minus omega t. Any of these equations can be used to represent a progressive wave along the plus x direction. Okay. Now our next task is to obtain an expression for a differential equation for this progressive wave. Okay. So we need to derive a wave equation. Wave equation in one dimension, of course. Okay. So let us start with the expression for traveling wave. We can use any one. Consider a wave moving along the plus x direction. So let me use equation 1. So we have the wave function is here, a sine. We can as well use cosine function, 2 pi by lambda x minus vt, right? So we need a differential equation for this wave. Okay, the solution is this. The solution of that differential equation must be this. So we need a differential equation which is satisfied by this wave function. Okay, so let us try with the space derivative first. So find dou y by dou x. I am using partial derivative because y depends on both position and time. So first derivative in position is the sine function will become cos function, and the coefficient of x will come out. The coefficient of x is this 2 pi by lambda. Okay, so what you get is this 2 pi by lambda will come out. Okay, a is again a constant, and sine function will become cos function. Derivative of sine theta is cos theta. Okay, take one more derivative. So second derivative with respect to x. Now the derivative of cosine function is minus sine function. Again the coefficient of x will come out. 2 pi, one more 2 pi by lambda. So we have 2 pi by lambda square, and we have a minus cosine, minus sine function. So minus a sine 2 pi by lambda x minus vt. Okay, so we start with equation 1 and we reach here. Let us call it equation 2. Okay, earlier I have used equation 2 and 3. Don't worry about that. Let us start the numbering freshly. Okay. Now, okay, so we have done second derivative in position. Let's go back to equation 1. This time let us take a time derivative. Once dou y by dou t. Again, derivative of sine function is cosine function, and the coefficient of time will come out. What is the coefficient of time? 2 pi by lambda is there, and also minus v is also there. So 2 pi by lambda times minus v will come out. So what you have here is minus 2 pi by lambda times v. The remaining part is a is constant, there is no change. Sine function becomes cos function. Cos 2 pi by lambda x minus vt. Take one more derivative. Okay. So dou square y by dou t square. Now we have a cosine function here in dou y by dou t. Derivative of cosine function is minus sine function. So there is an extra minus sign, and here also the coefficient of t should come out, which is 2 pi by lambda into minus v. So two minus signs are there. One comes from minus sine theta, the other comes from minus v. Okay, the two minus signs will cancel. So what you get is, already we have a minus sign here, minus 2 pi by lambda, two terms are here, 2 pi by lambda into 2 pi by lambda, 2 pi by lambda square. V into v becomes v square, a sine 2 pi by lambda x minus vt. Okay, the negative sign from sine theta and the negative sign from velocity v, the coefficient of t will have cancelled out. Let us call it equation 3. Now we want to connect the space derivative and position derivative with respect to position and derivative with respect to time. Look at equation 2 and equation 3. We have a minus sign, right? Look at the right side, minus sign is there, 2 pi by lambda square is there. In equation 2 we have a sine 2 pi by lambda x minus vt. In equation 3 also we have a sine 2 pi by lambda x minus vt. So what is additional term in equation 3 is a v square. So if you divide equation 3 with v square, we get equation 2. So the connection between these two, equation 2 and 3, together give you the result that dou square y by dou x square is equal to 1 by v square dou square y by dou t square. Right? Just divide equation 3 by v square, we get equation 2. So this is, let us call it equation 4. This is the differential equation for wave motion along x direction, along any one direction. Okay, this is called wave equation in one dimension. Wave equation in one dimension, because we have considered only propagation along the x-axis only. What is the wave equation for a wave propagating along 3 dimensions? Then on the left hand side, this wave function y will depend upon x, y and z. Okay, maybe we have to use another symbol for the wave function. Maybe we can use psi then. Okay, so that wave function will depend on x, y and z. Then instead of so maybe let's use another symbol for that wave function. Let us say psi. Then we have dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. So second order derivative in x, y and z. This psi is the wave function. I have, instead of y I have used psi. This is equal to 1 by v square dou square psi by dou t square. This is the wave equation in 3 dimension. Okay. There is a shorthand notation for this derivative with respect to x square, y square and z square. We use a symbol like del square psi. So del square psi equal to 1 by v square dou square psi by dou t square. Okay. That is only a shorthand notation. Instead of you writing dou square by dou x square plus dou square by dou y square plus dou square by dou z square, we can use this symbol del square psi. That's called a Laplacian operator. Okay, that is another matter. That's only a matter of notation. Let's don't worry about it now. So let's come back to our one-dimensional wave equation. So this is the one-dimensional wave equation. Okay, dou square y by dou x square equal 1 by v square dou square y by dou t square. Y is the wave function and x is the position and t is the time. V is the wave velocity or phase velocity. Let's try to understand what is the nature of this equation. Before that, let's ask a question here. So we have taken second derivative with respect to position and second derivative with respect to time. One can ask the question, what is wrong with the first derivative? For example, if you look at dou y by dou x here, it's 2 pi by lambda a cos 2 pi by lambda x minus vt. Dou y by dou t, here it is minus 2 pi by lambda v a cos. So both are 2 pi by lambda is there, cosine term is there, the additional term here is v. So if we divide this dou y by dou t with minus v, okay, then we get dou y by dou x. So another candidate for the wave equation is dou y by dou x is equal to minus 1 by v dou y by dou t. This is also a possible candidate for the wave equation. Why don't we use this? Look at here again. See, if we take dou y by dou t and divide with minus v, okay, that is or multiply with minus 1 by v, minus will cancel, v will cancel, we get exactly dou y by dou x. Okay, so this is also a wave equation, we can say. It connects derivative, first derivative in x, first derivative in position, or first derivative of with respect to position of the wave function with first derivative of wave function with respect to time. So what is wrong with this wave function, wave equation? The problem is it's okay, but the problem is this. If we consider the wave equation given by equation 4, okay, we have started with a wave traveling along plus x direction, right? Suppose we start with a wave traveling along minus x direction. Okay, that is, then the wave function will be y is equal to a sine 2 pi by lambda x plus vt, right? When you repeat this procedure, this you can do as a homework. Start with a wave traveling along plus minus x direction. Your starting wave function will be a sine 2 pi by lambda x plus vt. Do all these steps. First derivative, take dou square y by dou x square, dou square y by dou t square. Then you will see that the equation will be the same. This equation, wave equation, will be the same. Dou square y by dou x square equal to 1 by v square dou square y by dou t square. That means this equation is valid even if our starting wave is a wave traveling along plus x direction or minus x direction, or even if a wave traveling along any direction. If it is a wave traveling along any direction, you get a three-dimensional wave equation like this: del square psi equal to 1 by v square dou square psi by dou t square. So this structure of this equation, equation 4, is independent of our whether the wave is traveling along any particular direction. Whereas when you come to this equation, dou y by dou x equal to minus 1 by v dou y by dou t, this equation is satisfied by only by a wave traveling along plus x direction. If you start with a wave traveling along minus x direction, you will end up with an equation dou y by dou x equals 1 by v dou y by dou t. So it looks like you have a wave equation for a wave traveling along plus x direction, another wave equation for a wave traveling along minus x direction. There is a difference in sign, right? So this is not satisfactory. If we say that we have a wave equation, then it should be valid for all waves traveling along x direction, whether it is plus x direction or minus x direction. So if we say that we have a wave equation in one dimension, it should be satisfied by waves traveling along one dimension. Yes, whether the direction is plus x or minus x, the wave equation should be the same. So this is not a general wave equation, even though there is a connection between space derivative or position derivative of wave function and time derivative of wave function. This is not satisfied by all waves in one dimension. So this is not acceptable to us. Okay, what we need is a universal equation applicable for all waves in one dimension, and equation 4 is just that equation. Okay, that is why we go to second derivative. So you should check that this same equation is obtained by a wave traveling along minus x direction. That's it. Now let us come back to equation 4. Let us see what are the properties, what is the nature of this equation. This equation, let me rewrite this equation here. So the wave equation is dou square y by dou x square equals 1 by v square dou square y by dou t square, right? When you try to memorize this formula, sometimes people get confused whether it is 1 by v square dou square. Where does this 1 by v square appear? Whether it is along with dou square y by dou t square or dou square y by dou x square. Okay, in some books, instead of 1 by v square, they say v square times. So you can try to remember in any one way, right? So let us look at this formula 1 by v square. So if you try to recall, sometimes people get confused. What is the wave equation in one dimension? Is it 1 by v square dou square y by dou x square equal to dou square y by dou t square, or is it dou square y by dou x square equal to 1 by v square dou square y by dou t square? Where does this 1 by v square appear? Now when you look at this derivation, then it's natural that 1 by v square appear along with dou square y by dou t square. But when you try to write it down for the first time, or somebody asks you what is the wave equation in one dimension, then it may be confusing sometimes. There is an easier way to remember this. Look at the dimension on both sides. Okay, the wave function, let us say it's just a function. Let's don't worry about okay, when you write wave function like this, it's a number, right? Wave function, it's a sine function. What you get is a number. Okay, so wave function doesn't have any dimension per se. So what is the dimensional quantity involved here? On the left hand side we have dou square by dou x square. That means 1 by L square. 1 by L square, 1 by length square. Length square comes in the denominator. So on the right hand side also the dimension should be 1 by length square, right? Now we know that there should be a dou square y by dou t square term here. Okay, that we know. There should be a dou square y by dou x square term, second order derivative in position, second order derivative in time. So on the right hand side we have a 1 by t square comes dimension. But the dimension on the left side is 1 by L square, dimension on the right side is 1 by t square. Then the two dimensions should be the same because it's an equation. How do we make it happen? We know that when you multiply velocity with the time, we get length. Velocity into time is length. So there should be velocity square in the denominator. See, when velocity square is multiplied by time square, we get velocity into time square. Velocity into time is length. Length square comes in the denominator. So left hand side the dimension is 1 by length square. Right side only you get 1 by length square only if you have 1 by v square on the right side. So if you think, make this is called some dimensional analysis. If you make this dimensional analysis, it's easy to remember that 1 by v square should come along with dou square y by dou t square. Okay, so let us see what is the nature of this equation. This equation is a linear equation. Okay, it's a second order equation. Then it's a homogeneous equation, and it's a partial differential equation. Partial differential equation. So these are the attributes or properties of this equation. Sometimes we use the short form PDE to talk about partial differential equation. So this is a linear second order homogeneous partial differential equation. Let us look at each property. Why is it called a linear differential equation? Why is it a linear equation? It's linear because each term, the power of each term is 1. The power of each term in this equation is 1. See, what are the different terms? There are only two terms here. Dou square y by dou x square. That is one term. What is the power? 1. Derivative is, second order derivative is there. That is another thing. But the power raised to 1. Okay. And the second term on the right side, the term on the right side is 1 by v square dou square y by dou t square. The power is 1. So, each term contains either we can say that the power of each term here is 1. Okay, this is why it's called a linear differential equation. The power of I should say the power of each term containing the unknown function, okay, is 1. That's it. For example, there is a 1 by v square. I am not talking about that. Okay, the term containing either the unknown function y or its derivative. Okay, its power is always 1. That's why it's a linear equation. If the equation is of form like dou square y by dou x square, the whole square or whole cube, it's not a linear differential equation. It's a non-linear equation. So that is why if the power of each term is containing the unknown function is 1. Then it's called a linear differential equation. Now, why is it a second order equation? Second order because the highest derivative is 2. Here the two terms contain second derivative. There are no terms with first derivative or no terms containing simply the function, unknown function y. The power of the highest derivative is 1. If there is dou cube y by dou x cube, then it's a third order equation. If this equation contains only dou y by dou x, then it's a first order equation. For example, the other candidate that we considered for wave equation, dou y by dou x equal to minus 1 by v dou y by dou t. This is a first order equation. Okay, but since it is not a universal equation, universal wave equation applicable to all waves in one dimension, that's why we have not considered it. Okay, so this is a second order equation because the power of the highest derivative is 1. Why is it a homogeneous equation? Because homogeneous equation because every term contains either the unknown function y or its derivative. Every term contains either the unknown function y is the unknown function, right, or dependent function. X and t are independent variables, right? So this unknown function y, it appears in every term. Either y appears or its derivative appears. So every term contains either the unknown function or its derivative. Then such an equation is called homogeneous equation. We will see at least one counter example. So if there is a term which is independent of y in this equation, then it's a non-homogeneous equation. Okay. Regarding homogeneous equation, I should add one more point. Sometimes when you ask people what is a homogeneous equation, they say that if an equation contains 0 on the right side, it's a homogeneous equation. If it is not 0 on the right side, it's a non-homogeneous equation. But you should understand that any equation you can rewrite it in such a way that there is 0 on the right side. You can take all the terms to the left side, put a 0 on the right side. Okay, so that is not the condition for a homogeneous equation. Sometimes homogeneous equations are written like that, but for example, look at here, wave equation you can perfectly write like this. There is a term on the left side, there is a term on the right side. This is a homogeneous equation. If you want, you can take the term on the right side to the left side. You can write dou square y by dou x square minus 1 by v square dou square y by dou t square equal to 0. But whether you write 0 on the right side or not, homogeneous is an independent idea. Okay, because we can always make right hand side equal to 0 in any equation. So homogeneous means every term contains either the unknown function y or its derivative. It is there in every term. See, every term, the term on the left side contains second derivative of y, term on the right side contains second derivative of t. So it's a homogeneous equation. Why is it a partial differential equation? Because the unknown function y depends on more than one variable. In this particular case, unknown function y depends on x and t. So when you take the derivative, what you do is, when you take a derivative with respect to x, what you do is you keep the variable time constant and you differentiate with respect to x only. That means, in other words, it's a differentiation in part, or it's a partial differentiation. Okay, you are keeping one variable fixed and you are differentiating only with respect to the other variable x. That is why we use a different symbol. In fact, this is we can also call it we can also pronounce it as d square y by dx square, but we use a slightly tilted symbol for derivative, dou square y by, and call it dou square y by dou x square. Many people call it d square y by dx square itself, but just use the symbol, tilted symbol, to show that it's a partial derivative. Okay, so it's not because we are using the symbol, that tilted symbol, that it's a partial derivative. It's because y depends on more than one variables, and when you take differentiation with respect to x, we are differentiating, we are keeping the other variable constant, and we are doing a partial differentiation. Okay. Similarly, when you differentiate with respect to time, you can call it d square y by dt square, but we use a tilted symbol to show that this is also a partial differentiation. We are keeping the variable x constant and differentiating with respect to time only. So this is it. This wave equation is a linear, second order, homogeneous partial differential equation. Now I hope you understand why the different attributes are there. Now let us, before moving on with this wave equation and other points in this unit, let us pause here and consider a few more examples that we have already studied in differential equations, and see whether these four properties, linear, second order, homogeneous, and partial differential equations, these are satisfied by, or how these properties are attributed to the other differential equations that we have studied. For example, in the previous unit, linear harmonic oscillator, we have studied differential equation for undamped oscillator or ideal harmonic oscillator. See, so let us consider a few more examples, other examples of differential equation. So first I am considering differential equation for an undamped oscillator. This is also called the differential equation for simple harmonic motion, which it is mass into acceleration m d square x by dt square equals, for an undamped oscillator there is no damping force, only force is restoring force, which is minus kx. Okay, this you can also rewrite as you can divide throughout with mass, and you write this as d square x by dt square equal to minus k by m into x. Minus k by m is called omega 0 square. Okay, we can also write like this. So this is the differential equation of an undamped oscillator, or this is the differential equation of a particle undergoing simple harmonic motion. How do we explain, or what are the properties of this differential equation as far as we have concerned? You can see that the power of every term is 1, right? Left hand side d square x by dt square, its power is 1. Right side you have minus omega 0 square x, its power is also 1. So or maybe I should say power of, instead of power of each term, I should say the power of the unknown function and its derivative is 1, right? So on the right hand side again you have this confusion, omega 0 has the power 2. So the point is, look at the unknown function x. Here the unknown function is x, or the dependent variable is x, dependent function is x. the unknown function x has the power 1. On the left hand side, its a second derivative is there, d square x by dt square, but its power is also 1. If you look at the wave equation, 1 by v square, this 1 by v square, this has a dimension, power 2. But what you are interested in is look at this, the derivative of y, dou square y by dou x square, its power is 1. Derivative of y on the right side, time derivative of y on the right side, dou square y by dou t square, its power is also 1. In the same way, here the unknown function x has the power 1. On the left side, unknown function d square x, the second derivative of unknown function d square x by dt square is also 1. So it's a linear equation. Okay, and the highest derivative is 2, so it's a second order equation. And then every term contains either the unknown function x or its derivative, so it's a homogeneous equation. Again, you see that if you want, you can make the right hand side 0, but it's not necessary. Every term, so the term on the left side contains the second derivative of x, the term on the right side contains x itself. So every term contains either x or its derivative, so it's a homogeneous equation. And it's not a partial differential equation because x depends only on time. So we take, when you differentiate with respect to time, it's an ordinary differentiation. So this type of a differential equation is, we can say, linear second order homogeneous ordinary differential equation. Okay, ODE, ordinary differential equation. Okay, let us consider two more examples. Now, again from previous unit, harmonic oscillator. Consider a damped harmonic oscillator. What is the differential equation of a damped harmonic oscillator? In damped harmonic oscillator, again the force, that is mass into acceleration, it contains, there are two terms here, two forces here. One is the restoring force, which is minus kx. The other is the damping force. This damping force is proportional to the velocity and it's opposite to the direction of velocity, so there is a minus sign, and the proportionality constant we have taken as b. So we get an equation like this. If you want, you can divide throughout with mass, and k by m you can write as omega 0 square, b by m you can write as gamma. Okay, this is sufficient. And look at this equation. Again, all the terms, every term contains, in every term, the power of the unknown function or its derivative. Look at d square x by dt square, its power is 1. Look at x here, its power is 1. Look at dx by dt, it contains all the derivatives. Its power is also 1. So power is 1. So this is a linear equation. This is linear. The highest derivative is 2. See, you have x here, dx by dt here, d square x by dt square here. Highest derivative is 2, so it is again second order. And every term contains either the unknown function x or its derivative. See, second derivative, the function, unknown function x, first derivative. So every term contains either x or its derivative, so it's homogeneous. Again, I am not purposefully writing homogeneous equation. I'm not writing it as in such a way that the right hand side is always 0. In order to convey the idea that right hand side need not be 0, you can write it in any way. And again, you see that this is an ordinary differential equation, not a partial differential equation, because x depends only on time. Okay. And lastly, let us consider a forced oscillator. Okay. So a forced damped oscillator. A forced oscillator, that means an oscillator driven by some external force, and there is also damping force. So how do you write the differential equation? Mass into acceleration is equal to, what are the different forces here? Of course, restoring force is there, damping force is there. In addition, a driving force is also there. Let's assume that this driving force is harmonic. It is a harmonic force. So let me write this as f0 cos omega t, where omega is the frequency, driving frequency of the force. So this is the differential equation for a forced damped oscillator. Now, how do we uh, explain this? What are the attributes? So, in every term, the unknown function or its derivative, its power, look at it, d square x by dt square, power is 1, x power is 1, dx by dt power is 1. In the last term, there is no unknown function, so let's don't worry about its power now. So, if, when wherever the unknown function or its derivative is present, power is 1. So, this is a linear equation again. This is linear. The highest derivative of the unknown function is 2, so it's second order. Now here, does every term contain the unknown function or its derivative? No, because here you have second derivative, here you have the unknown function x, here you have first derivative. But look at this formula, this part, f0 cos omega t. This doesn't contain the unknown function x. So you have a term that doesn't contain the unknown function. This is called a non-homogeneous term. This term is called a non-homogeneous term, or another word is source term. In the terminology of differential equations, this is called source term. So when such a source term which doesn't contain unknown function is there, it's a non-homogeneous differential equation. So this is non-homogeneous. Okay, and it's ordinary differential equation, not a partial differential equation. So even non-homogeneous differential equation, for those who are worried that homogeneous equations right hand side should be 0, for non-homogeneous equation right hand side is non-zero. See, here also you can take all the term to the left side and keep the right hand side 0. So whether right hand side is 0 or not is immaterial. What's important is this: do you have a source term that doesn't contain the unknown function? Then it's a non-homogeneous equation. Okay. So these are three examples that we have already seen in harmonic oscillator. Let's come back to our wave equation in one dimension. Dou square y by dou x square equal 1 by v square dou square y by dou t square. So as we have noted, it's a linear second order homogeneous partial differential equation.